In our previous videos, we defined what we call the cumulative distribution transform. And as a quick review, the cumulative distribution transform is a mapping from the space of probability density functions to the space of diffeomorphisms. And we compute this mapping by matching a given signal probability density function S of x to a reference signal which we call S naught of y. This matching is computed by matching their cumulative distributions. That is, if we integrate, for example, S naught here from minus infinity to some value y, we seek what is the value S hat of y that we have to integrate the same function but on the S domain, right? If we integrate S domain, integrate S naught domain, we get their cumulative distributions, and we are asked to find the value that corresponds to y on the S naught side, and we call that corresponding value S hat, and that's how we defined the transform. So if we call the cumulative distribution of S as a capital S, little s is the signal, capital S is the cumulative distribution, we derived this formula. And if we plug in the uniform distribution for little s naught, then capital S naught of y will become just y, and hence the cumulative distribution of S with respect to the uniform distribution is simply the inverse of the cumulative distribution of S, right? And this mapping has a forward formula that you can go from S to S hat, as well as an inverse formula where you can go from S hat to back to S with the knowledge of the reference. So in this video, what we're going to do now is walk you through how one could do these computations in the computer, and then we'll show you the Pytranskit CDT class that performs this computation. So let's begin. Let's say you have a signal, and for the time being, we're going to define the signal to be z of x as a Gaussian probability distribution function, right? You should be familiar with this. The mu here is the mean of this Gaussian function, and the sigma squared here is the standard deviation. This is how we can code such a function in Python. For example, we come up with an independent variable x, which is going to become an array between 0 and 1. We have 500 points. Well, let's say sigma is 0.1 here. That's standard deviation, and the mu is essentially halfway, 0.5, halfway between 0 and 1. And here is the Gaussian function coded that codes exactly this function over here, and here's how this Gaussian is plotted. So now to compute the CDT of this Gaussian function digitally, the first step is to normalize the z array so that when we sample this Gaussian function, we'll have an array, which is z here. We plot x and z, but this array, when it's digitized, it may not sum exactly to 1. So we divide the array z by the sum of z, and so we call that the signal S of x, and this sum of x now will become exactly 1. For reasons we'll talk about in a second, we also we'll add an epsilon, a very tiny 1 to the minus 7 epsilon to our function z here, so that the minimum of our signal is not 0, but something slightly above 0. So here's, again, it's imperceptible to the human eye. You can't tell really the difference between our original signal and the normalized signal. So now we're asked to compute the integral of our signal, right, with capital S, and the integral can be computed of an array can be computed by the cumulative sum. So this function here in Python, cumulative sum, computes the cumulative distribution of our signal S, and here is the plot. Now, how can we compute our CDT as we defined over here, right? Using a uniform reference requires us to invert obtain the functional inverse of this cumulative distribution, capital S here. So how can we do this? So if we note here, let's zoom into this cumulative function here, let's say between 0.3 and 0.8, and let's imagine, because we have our S array, it's an array of finite number of values. So in other words, it's a digital signal which has been turned into a digital cumulative distribution. And if we plot just a few of these values, 0.3, at 0.4, 5, it's 6, 7, 8, and so on, we'll see the values corresponding in the y-axis, right? So the x-axis is the independent variable, the x values, and the y-axis here corresponds to the values of capital F's of x, or the cumulative distribution of f. And as we can see here, the signal is regularly sampled in the independent variable domain here. So we have samples at 0.3, 0.4, 0.5, 0.6, 0.7, 0.8 at equally spaced intervals of 0.1. Of course, in the simulation we have more samples than that, but I'm grabbing every 50 samples or so to make the point. So while this variable here is regularly sampled, you can see the value of the accumulation is irregularly sampled, right? The first value here is 0.0236, the second one is 0.1631, the third one is already 0.5080. So there is no regularity here, right? And to obtain the inverse of this function, in theory, all we have to do is flip this axis, right? So if here we're plotting, for example, as x, which is the independent variable, and the dependent variable is the CDF of s, right? X and y is the CDF or s CDT. The inverse is the opposite, where in the independent variable we'll put s CDF and in the dependent variable x. So in theory, by the sampled arrays themselves, we can just flip the order and interpret the signals as the inverse. But of course, if we would like to do any computations in transform domain, like add two transforms, take their inner product, multiply by a matrix, and so on, it will help if we have the definition on a fixed grid of the inverse function. In other words, we have to put these values here now on a regular grid. How can we do this? Well, we're just going to imagine that we fit an interpolating function across all of these points over here, and then we, on a regular grid here, we just grab the values of this interpolating function. Luckily, Python has a nice convenient function, or NumPy I should say, has a nice convenient function for us to compute this interpolation. And the way this function works, here you can have the documentation for it, right? So it requires you to input three values. The second value is the independent variable, and the third value is the dependent variable evaluated at your independent variable. The first value is where you would like to evaluate this interpolation. And of course, you can specify certain other criteria like the interpolation method and so on. Right, so our job was to regrid essentially this y coordinate here so that it's gridded on a regular grid. So first thing we do is we create a regular grid on the y coordinate, and then we simply call this interp function in Python, where again we pass the independent variable, which again in the inverse signal is our SCDF, right? And the dependent variable now has become our x. But again, this independent variable is irregularly sampled, so we would like to evaluate it at the regular samples, and this is what we call the CDT of s, right? So here is the plot of the original function s and the CDT of s. The inverse transform, as defined here, can be obtained similar with interpolation. First, we need to compute the inverse of our CDT and differentiate, and then evaluate our original function, our original reference function, which is our uniform function in this particular example we're showing, at this inverse function, right? So the Python calls following a very similar logic to what we just described are over here. So first we obtain the f prime, right? And 1 over f prime is essentially the f prime of the inverse, right? This can be shown mathematically, and then we simply interpolate at our original sample value x, and then we can get our signal back s, and we can compare to the original signal. So this is how one would do it, but luckily we have in our Pytranskit software package, if you go to the Pytranskit website, here it is, and you scroll down to the CDT section, you can click into one of these notebooks, download the notebook as that shows you an example of how to run the CDT code, right? So you import NumPy, etc. You create here your reference signal, and here again we give an array, but this is just an implementation of the uniform distribution. And here we create another Gaussian signal to demonstrate. Now we normalize both the reference and our array. Now we import the CDT class, instantiate it, and then we just call CDT forward that performs these operations that we just described. There are 4 parameters. You must pass the independent variable of your reference, and then the independent variable signal and your signal, and this will output your I-hat, which is your transform. This is an old definition that from one of our first papers, so you can disregard that for now. So if you just call this code and then the rest plots it, so you can see your original signal and you see the CDT. Once again, all you need to do is type cdt.forward and pass in the necessary arrays. Similar business with the inverse here. We've decided that to set the first value to exactly 0, because remember we added an epsilon, so if we reconstruct we're not going to get exactly the signal, but something shifted, so we fix that first, and then we just type CDT inverse and it will obtain the inverse CDT. This notebook also goes ahead and demonstrates the different mathematical properties that we derived in our previous video. Here is the translation, right? So we have 2 signals here. One signal is I1 and I2, and these are translated versus with respect to one another, translated in the independent variable axis, right? So translation in the independent variable becomes translation in the dependent variable, as we already covered. Here's a scaling property, similarly described as before. And finally, the linear separability property, right? So here this code simulates a series of signals for 3 classes, for example. Class 1 has 1 bump, class 2 are signals of 2 bumps, class 3 are signals of 3 bumps. And let's say they can be randomly shifted within our domain. Here are the corresponding CDTs, and the argument here is that while this is not linearly classifiable in signal domain, in transform domain it becomes perfectly linearly classifiable. Here's some code that performs linear classification of test samples. Again, we must always separate training and test samples, and if you project test samples on the linear classifier in signal domain, you get somewhat of a mess, and if you project test samples on the classifier obtained in transform domain, you obtain very nice separability.